Programmable logic control. All programmable logic controls have four basic components. The four basic components of a programmable logic controller include the power supply, input and output section, processor section, and programming section. Programmable controller section, processor section, number 3. Input and output section, number 2. Power supply, number 1. Programming section, number 4. The four basic parts of a controller include the power supply, input and output section, processor section, and programming section. The programs used for discrete parts manufacturing and process manufacturing are stored in and retrieved from memory as required. Programmable logic controller components are interconnected and work together to allow the controller to accept inputs from a variety of sensors, make a logical decision as programmed, and control outputs such as motor, starters, solenoids, valves, and drives. Power supplies. The power supplies provides the necessary voltage levels that are required for the internal operation of the programmable logic controller. In addition, it may provide power for the input and output modules. The power supply can be a separate unit or built into the processor section. It takes the incoming voltage, normally 120 volts AC or 240 volts AC, and changes the voltage as required, normally 5 volts direct current to 32 volts direct current. The power supply must provide constant output voltage free of transient voltage spikes and other electrical noise. The power supply also charges an internal battery in the programmable logic controller to prevent memory loss when external power is removed. The operation life is lithium batteries, which are commonly used as power supplies for programmable logic controllers, is from 3 years to 5 years. Input and output sections. The input and output section functions as the eyes, ears, and the hands of a programmable logic controller. The input section is designed to receive information from push buttons, temperature switches, pressure switches, photoelectric and proximity switches, and other sensors. The output section is designed to deliver the output voltage required to control loads such as alarms, lights, solenoid, and starters. The input section receives incoming signals, normally at a high voltage level, and converts them to low power digital signals that are sent to the processor section. The processor then registers and compares the incoming signals to the program. The output section receives low-power digital signal from the processor and converts them into high-power signal. This high-power signal can drive industrial loads that light, move, grip, rotate, extend, release, heat, and perform other functions. The, in, the input and output section can either be located on the programmable logic control on board or be part of expansion modules. On board, input-output are a permanent part of the programmable logic control package. Expansion modules are removable units that include inputs, outputs, or combination of its inputs and outputs. Onboard input-output usually include a fixed number of inputs and output that define the limits of the programmable logic control. For example, a small programmable logic control may include up to 16 inputs and 8 outputs. This means that up to 16 inputs and 8 output may be connected to the controller. Programmable logic controller that use expansion modules allow the total number of input and or output to be changed by changing or adding modules. On board, programmable logic control are normally used for individual machines and small systems. Expansion programmable logic controllers are normally used for large system or small system that require flexible changes. Discrete input-output section. Discrete input-output section are the most common inputs and outputs. Discrete input and output use bits that represent a separate and distinct signal each, such as on and off, open close, or energize or de-energize. The processor reads this as the presence or absence of powers. Example of discrete input are push buttons, selector switches, joystick, relay contact, starter contact, temperature switches, pressure switches, level switches, flow switches, limit switches, photoelectric switches, and proximity switches. Discrete outputs include light relays, solenoid, starters, alarm valve, heating elements, and motors. Data of input and output section. In many applications, more complex information is required than the simple discrete input-output is capable of producing. For example, measuring temperature may be required as an input into a programmable logic control, and numerical data may be required as an output. Data input and output section are inputs and output that produce or receive a variable signal. They may be analog, which allows for monitoring and controlling analog voltages and currents, or they may be digital, such as binary coded decimal input and output. When an analog signal such as voltage or current is input into an analog input card, the signal is converted from analog to digital by an analog to digital converter. The converted value, which is proportional to the analog signal, is sent to the processor section. After the processor has processed the information according to the program, the processor output the information to a digital to analog converter. The converted signal can provide an analog voltage or current output that can be used or displayed on an instrument in a variety of processes and application. Example of data inputs are potentiometers, rheostats, encoders, barcode readers, and temperature, level, pressure, humidity, and wind speed transducers. Example of data outputs are analog meter displays, digital meter display, stepper motor signal, variable voltage outputs, and variable current outputs. Input and output capacity. The size of a programmable logic control is based on the input and output capacity. Common input-output capacities of different sizes of programmable logic controllers include the following: mini and micro, 32 or fewer input-output section but may have up to 64. Small, 64 to 128 input and output section but may have up to 256. Medium, 256 to 512 input and output section but may have up to 1,023. Large, 1,024 to 2,048 input and output section but may have many thousand more on very large units. The input and output section may be directly connected to the programmable logic control or may be in a remote location. Input and output section in a location remote from the processor section can be hardwired into the programmable logic controller, multiplexed over a pair of wires or sent by a fiber optic cable. In any case, the remote input and output is still under the control of the central processor section. Common programmable logic controller may have 16, 3264, 128, or 256 remote input and output section. Fiber optic communication modules route signals from the inputs to the processor section and then to the outputs. Fiber optic communication modules are unaffected by noise interference and are commonly used for process application in the food and petrochemical industries. They are also used in hazardous locations. Solid-state input control. Programmable logic control can have many types of inputs including push buttons, level switches, temperature control, and photoelectric controls. Inputs such as push, but, push buttons and temperature controls are normally easy to input. However, more complex solid-state control inputs such as proximity and photoelectric switches inputs required special consideration because of their function. Solid-state proximity and photoelectric controls are used in many automated systems. See in Figure 2, these controls normally have a solid-state output that is ideal for input into programmable logic control. Photoelectric control can be input into a programmable logic controllers for detection, inspection, monitoring, counting, and documentation. Available outputs include 2 and 3 wire types with thyristor and transistor output that can be connected individually or in series or parallel combination. This is the figure solid state proximity controls. Proximity controls. Figure 2. Solid-state proximity controls normally have a solid-state output that is ideal for input into programmable logic control. The leakage current problem can be corrected by placing a load resistor across the input device. See in Figure 4. The resistor value should be chosen to ensure that a minimum load current is exceeded and the effective load impedance is reduced. This prevents of state leakage current turn on. This resistance value is normally in the range of 4.5 4.5 k ohms to 7.5 k ohms. A general rule is to use a 5,000 ohms 5 watts resistor for most application. Two-wire thyristor outputs. Two-wire thyristor outputs are available in a supply voltage range of 20 volt alternating current to 270 volts alternating current at about 180 milliampere to 500 milliampere range in either no or N- NC versions. Two-wire thyristor outputs have only two wires and are wired in series with the load, which is similar to a mechanical switch. See in Figure 3. The power two-wire thyristor output sensors is received through the load when the load is not being operated. As with any thyristor output device, some consideration must be given to off-state leakage current and minimum load current. Unlike a mechanical switch, the proximity sensor consumes current in active mode. The current is small enough that most industrial loads are unaffected. However, this leakage current may be enough to activate the load on some high impedance loads and controllers. This is the figure 3. Two-wire thyristor output. Two-wire thyristor output have only two wires and are wired in series with the load, which is similar to a mechanical switch. Load resistor. 24 volts, two-wire DC output. Input voltage. Input module. Input. Load resistor. Leakage current path. Figure 4. A load resistor may be required when connecting a sensor to the controller to prevent leakage current from being input into the controller. Electrical noise suppression. Electrical noise is unwanted signals that are present on a power line. Electrical noise enters through input device, output device, and power supply lines. Unwanted noise pickup may be reduced by placing the programmable logic control away from noise-generating equipment such as motors, motor starter, welders, and drives. Noise suppressions should be included in every programmable logic control installation because it is impossible to eliminate noise in an industrial environment. Certain sensitive input device, analog and digital, require a shielded cable to reduce electrical noise. A shielded cable used an outer conductive jacket shield to surround the two inner signal-carrying conductors. The shield blocks electromagnetic interface. The shield must be properly grounded. To be effective, proper grounding includes grounding the shield at only one point. A shield grounded at 2 points tends to conduct current between the two grounds. Low voltage direct current signals must not be routed near high voltage 120 volts alternating current signals. If the signal must cross, it is important to ensure that the cable cross at 90 degree to minimize interference. See in figure 5. This is a figure 5 shielded cable. Braided shielded cable to signal source sensor to PLC input card or receiver. There's a ground cable at one end only. Next, two source, two receiver, two source, to receiver, to source, to receiver. Incorrect. Do not ground on both ends. Figure 5. A shielded cable uses an outer conductive jacket or shields that block magnetic interference from the two inner signal-carrying conductors. A high voltage spike is produced when inductive loads such as motors, solenoid, and coils are turned off. These spikes may cause problems in the programmable logic control. High voltage spikes should be suppressed to prevent problems. A snubber circuit is used to suppress a voltage spike. Typical snubber circuit use an RC or resistor or and capacitor, MOV metal oxide varistor, or diode, depending on the load. See in figure 6. Figure 6. Snubber circuit, output module. This is an output device. Small AC load, capacitor symbol, resistor, output device. DC loads, reverse bias diode, large AC loads. This is MOV, metal oxide varistor. Figure 6, snubber circuit are used to suppress voltage spike in controllers. Three-wire transistor outputs. Three-wire transistor outputs are available in a supply range of 10 volts direct current to 40 volts direct current at about 200 milliampere. These sensors are easily interfaced with other electronic circuitry and programmable logic controls. Output sensor type consists of either an open collector, NPN or PNP transistor, both normally open or normally closed version are available. This output device receive their power to operate through two of the leads, positive and negative respectively, from the power source. The third lead is used to switch power to the load either using the same source of power as the proximity switch or an independent source of power. See in Figure 7, 3-wire transistor output sensor. Sensor power source, positive. Load power source, positive, is NPN. Sensor common, negative or ground. Load common, connected together. Independent source, load, out, NPN. PNP. Current sinking, current sourcing, PNP. Next is to sensor voltage supply, negative and positive. NPN output, input module, right side. Processor section. The processor section is the section of a programmable logic controller that organizes all control activity by receiving inputs, performing logical decision according to the program and controlling the outputs. The processor section is the brain of the programmable logic controller and can be referred to as the central processing unit or CPU. See in figure 8. Processing section. This is a processor section. Figure 8. The processor section organizes all control activity by receiving inputs, performing logical decision, and controlling the outputs. The processor section evaluates all input signals and levels. This data is compared to the memory in the programmable logic controller, which contains the logic of how the inputs are interconnected in the circuit. The interconnection are programmed into the processor by the programming section. The processor section controls the output based on the input condition and the program. The processor continuously examines the status of the input and outputs and updates them according to the program. See in figure 9. Scan is the process of evaluating the input-output status, executing the program, and updating the system. Scan time is the time it takes a programmable logic control to make a sweep of the program. Scan time is normally given as the time per kilobyte of memory and is normally listed in milliseconds. Scanning is a continuous and sequential process of checking the status of inputs, evaluating the logic, and updating the outputs. This is the figure 8. Processor monitors inputs, input sections, and output sections. Output. Processor section. Time delay, logic functions, counting, compare, jump, register, latch, unlatch, shift, rotate, print, diagnostics, document, execution of program, interfacing, analog to digital, digital to analog, the status of of the inputs and outputs and updates them according to the program. The processor section of a programmable logic controller has different modes. The different modes allow the controller to be taken online, system running, or offline, system on standby. Processor modes include the program run and test modes. See in figure 10. The program mode is used for developing the logic of the control circuit. In the program mode, the circuit is monitored and the program is edited, changes saved and transferred. The run mode is used to execute the program. In the run mode, the circuit may be monitored and the inputs and outputs force program changes cannot normally be made in the run mode. The test mode is used to check the program without energizing output circuits or devices. And in the test mode, the circuit is monitored and inputs and outputs are forced in the program without actually energizing the load connected to the output. This is a processor mode. Programming terminal. Processor modes display on terminal. Mode equals program run test. Processor modes indicate by status indicators on controller. Programmable controller. Status. Power, PC run, CPU fault. Force, input output, battery low. Input. Figure 10. The processor section of a controller has different modes that allow the controller to be taken online. System running or offline, system on standby. Programming section. The programming section is the section of a programmable logic controller that allows input into the controller through a keyboard. The processor must be given exact step-by-step direction. This means things such as load, set, reset, clear, enter, in, move, and start timing must be communicated to the processor. The programming of a controller involves the programming device that allows access to the processor and the programming language that allows the operator to communicate with the processor section. Programming devices. Programming devices vary in size, capability, and function. Programming devices are available as simple, small text display units or complex color displays with monitoring and graphic capabilities. See in Figure 11. This is Figure 11, Programming Devices. Programming devices are available as simple, small text display units or complex color display within monitoring and graphic capabilities. Thank you.